This question is from GATE 2015 Mechanical Engineering paper, set 2, question number 50. The flow stress in megapascal of a material is given by sigma equal to 500 into epsilon raised to 0.1, where epsilon is true strain. The Young's modulus of elasticity of the material is 200 gigapascal. A block of thickness 100 millimeters made up of this material is compressed to 95 millimeters thickness, and then the load is removed. The final dimension of the block in millimeter is dash. What is given in the question is a cross section which had 100 millimeters thickness is compressed to 95 millimeters thickness. So the previous thickness it had was 100 millimeters, which is the initial thickness, and the final that it is having is 95 millimeters. So there is a reduction of 5 millimeters in the thickness, that is the material is being compressed. So we will have to use the compression relation between stress and strain and not the tension relationship. So keep that in mind for the first step. Now after compressing it, if the load is being removed, the strain part that will be regained will be elastic strain. Therefore, total strain has two parts, elastic strain and plastic strain. This will be permanent, while elastic strain will be regained after the load is removed. This elastic strain we will have to calculate and then see what is the change in length because of this elastic strain being regaining, and then add that change to 95 millimeters. This will give us the final dimension of the block in millimeters. Of course, dimension is to be written only in terms of thickness. Let's solve this. So first we will find out how much is the stress in the material when it is being compressed to 95 millimeters. For that we will have to use the given flow stress equation, that is sigma is equal to 500 times the true strain raised to 0.1. This is the true strain. In order to find the true strain, first we'll find the engineering strain, E. So the engineering strain E is nothing but change in thickness divided by the original thickness. Change in thickness is 95, the new thickness minus the original thickness 100 divided by 100. So this gives us as minus 0.05. Strain is unitless because it's the ratio of the same dimension. It is a pure number, minus 0.05. The negative sign indicates strain is compressive. From the engineering strain, we can find out the true strain. Epsilon, true strain epsilon is equal to natural log of final thickness by initial thickness. TF can be written as original thickness plus the change, and so we'll write this as ln of initial thickness by initial thickness gives us 1 plus changing thickness by original thickness gives us the strain E. By substituting minus 0.05 here, we get epsilon is equal to natural log of 0.95, which is nothing but minus 0.0513. We have the true strain. We can find out the stress in the material when it is strained at this value. So stress in the material sigma, compressive stress of course, will be equal to 500 into minus 0.0513 to the power 0.1. So compressive stress sigma is equal to minus 371.5196. If we write the nature, we need not show the sign, but we haven't written the nature, so we'll show the sign here. Now we have the stress in the material when it is strained to this value. After removing the load, there will be elastic recovery, and this elastic recovery will follow the path such that its slope will be equal to the initial slope. Let me draw the curve and show this to you. So we'll have stress and strain both in the negative side. This is the true stress, true strain curve. This curves look something like this. And if we say that this is the strain of 0.0513, which is a negative value shown as compressive. At this particular strain, the stress value in the material corresponds to 371.5196 megapascal. Stress is in megapascal. Now after it is being recovering, it will follow the slope of this initial elastic curve, slope of which can be found out using Hooke's law. So these lines will be parallel to each other when there is the elastic recovery. This being a right angle triangle, if you want to find out the strain that is being recovered, we can find out using Hooke's law, isn't it? Because this is a normal triangle and this slope will be equal to E, that is modulus of elasticity E. Therefore, we can equate the stress sigma is equal to modulus of elasticity E into the elastic strain that we want to find out, which will be recovered. Recovery strain is not 0.0513, but this value is the recovery strain, this much value. Let's find this out. It is 317.5196 is equal to modulus of elasticity is given to be 200 gigapascal. So we'll convert this to megapascal because stress is also in megapascal. So E is 200 into 10 to the power 3 megapascal into the elastic strain E. Therefore, elastic strain is equal to 317.5196 divided by 200 into 10 to the power minus 3. This comes out to be 1.857 into 10 to the power minus 3. This is the elastic recovery. So we can find out how much has the length changed for this elastic recovery. Now this elastic recovery is going towards the positive side, opposite direction to the compression, and because this is the elongation of thickness. Therefore, we can equate this to change in thickness when the elastic recovery takes place divided by the initial thickness. Now this time, this initial will be for the elastic recovery. So when the elastic recovery happens, the initial is 95 and we need to find out the change in thickness. Will be equal to the strain, which is 1.857 into 10 to the power minus 3. Therefore, the thickness that is recovered due to the elastic recovery will be 95 into 1.857 into 10 to the power minus 3. This is 0.17646 millimeters. Therefore, final dimension of the block will be, or final thickness of block will be 95 mm plus this elastic recovery 0.1765. So this becomes 95.1765 can be written as 95.18 millimeters. Let's fill in the answer. Final dimension of the block is 95.18 millimeters. To learn more about the flow stresses in materials, you can refer to the NPTEL video Lecture 23, Determination of Flow Stresses in Metalworking from the course Principles of Metal Forming Technology. It is by Professor P.K. Jha. He is from Department of Mechanical and Industrial Engineering, IIT Roorkee. I hope this solution will help you clear your doubt. Thank you.